So I give you another example where limit does not exist, and we will still be continuing with our graphical analysis. So I take another function which is very important in analysis, that is called signum function. Now this function is defined as fx equal to modulus x divided by x. Now you know this is the modulus function, absolute value function, and this is the identity function. Now you can write it a little differently, that this also means that fx is 1 when x is positive and fx is minus 1 when x is negative. Now I'll make a diagram of this. This means that if you take x here, when x is positive, this is 1, and when x is negative, this is minus 1. Now you check the limit of the function when x goes to 0. Now the concept that we have already done, that means that you have to check the limit by going to 0 from the right side and from the left side. Now see carefully, if you go to 0 from the right side, the function will get the value 1, and if you go to 0 from the left side, the function will jump on to minus 1. So the right hand limit will be 1 and the left hand limit will be minus 1. So again the two limits diverge, so we come to the conclusion that this limit also does not exist. So in this function, the signum function, and the last function, that the greatest integer function, we showed with the help of the diagram that the limit does not exist, because the point where we were investigating the limit, if we reach that point from the right, we reach somewhere else, and if we go to the point from the left, then we reach somewhere else. Alright. So this was the graphical analysis till now. But now I'll move to something serious, and students normally don't like these mathematical jargons or mathematical language as you call it, but I'll advise you to be familiar with this, because this you are going to encounter when you reach mathematics at the higher level. So till now we have told you that the limit exists. I made a diagram and I told you that check with this point, you check from the right, you check from the left, and you saw that the limit exists. But mathematics doesn't work like that. You have to justify that the limit exists. Now I'm going to explain the concept, which will also let you understand the definition of the limit and the justification behind limit. Now I'll start with the very first function that we took in the beginning. Now starting again at y equal to 5x, this is our function. Now I told you that this is y equal to 5x, this is our function, and I told you that when x goes to 5, the function gets the value 25. Now we wrote that the limit of the function when x goes to 5 is 25. Now how can you justify that? Now this is the limit, how can you justify that? Now you have to understand this concept very, very carefully. See, this value is 5, this value is 25. That is for sure. This is in front of you. Now let me do one thing. I'll take a slightly higher value as compared to 25. Let's say this is 25 plus 1 by 10. And I'll take a slightly lower value. This is 25 minus 1 by 10. So I have created what is called a neighborhood in mathematics. I have created a neighborhood. 25, I know that this is the limit. Here we will assume that we know the limit. Then we can take with, you can use the symbols. Now here I am working with the actual numerical value, that is 25. So I take a slightly higher value, let's say 25 plus 1 by 10, and a slightly lower value, that is 25 minus 1 by 10. Now my question is that corresponding to this neighborhood, can we generate a neighborhood here? Corresponding to this neighborhood, can we generate a side by side, you can call neighborhood here, so that if I give you the values from here, you get the values from there. Now let's see. Here it is obvious. So if I take some neighborhood here, means some larger values and some smaller values, so I consider the range from here to here. So for all these values, can I get a similar neighborhood here around 5, so that whenever I get a value here, I get a value here. Now in this case, so you can see that, you can tell that okay, this is obvious from the figure that there is a neighborhood here and there is a neighborhood here. But no, it will not work like this. You have to prove that there is a neighborhood here and there is a neighborhood here. I repeat, because this is important. This is the limit when x is having 5 value, this is 25, we know it. Now, justification part. We take a small deviation here, we take a small deviation here, 25 plus 1 by 10, 25 minus 1 by 10. I am saying that corresponding to this neighborhood, is there a neighborhood here, so that we have the points here and we could get the points here. Now how we can do that? Now there is a process to do that. Let's see how we do that. Now I'll tell you the trick also to do that. Now your function is fx, your limit is 25. Now say it carefully. Your function is fx and your limit is 25. Now you have to make your function deviate from the limit by 1 by 10. This should be clear to you. This is the function. Function is 5x. At a particular value, the limit is 25. At a particular value, the limit is at a particular value, the limit is 25. So now I make my function move away from 25 by 1 by 10 and by minus 1 by 10. So I can write like this. Fx minus 25 should be falling between 1 by 10 and minus 1 by 10. Now, what you have to do, that you have to manipulate this and you should reach x. You should do something so that in the inequality, between the inequality sign, you get x. Now, this is not difficult at all. You put 5x here because you know your function for sure. 5x minus 25, this should lie between 1 by 10 and minus 1 by 10. This is okay because here my function is 5x. So I'll deviate my function from the limit that I'm investigating, 25 by 1 by 10 and minus 1 by 10. Now, I can divide the entire inequality by 5. I told you that we need to go to x. So I divided by 5. So this becomes x minus 5 less than 1 by 50 and minus 1 by 50. So this is clear. So x minus 5 lies between 1 by 50 and minus 1 by 50. Now what is that? Check here. This is x equal to 5. This means I can take this to be 1 by 50 and I can take this to be minus 1 by 50. So I go by 1 by 50 to the right of 5 and I go by minus 1 by 50 to the left of 5. What is the interpretation? The interpretation is that, now you see very carefully, that if my function moves from 25 by 1 by 10, then my independent variable 5 moves by 1 by 50. So, for the movement of the function from the limit by the size 1 by 10 will require my independent variable to move from the limit point by 1 by 50. So there is a neighborhood of plus minus 1 by 10 and there is a neighborhood of plus minus 1 by 50. So if I can guarantee this as I have guaranteed in this case, then there is a limit. This is the logic behind the limit, that whenever, no matter how small neighborhood you can generate, you have a neighborhood here. And you see, there is some connectivity also. This is 1 by 10 and this is 1 by 50. Now let me make it more clear that whenever you generate a neighborhood here, you generate a neighborhood which is precisely 1/5 of this neighborhood. 150 is 1/5 of 110. So whatever deviation you make here, you have to make a deviation of 1/5 of that, and that will guarantee that if you take the values from in this neighborhood, you will get the values in this neighborhood. So this is exactly the meaning of limit. Now, I can use symbols. When you see the textbooks, they will use all sort of exotic signs, but that's not difficult. Let's see what we have done. Now, this x minus 5 less than 150 and 1 by 50 and minus 1 by 50, I can write it as x minus 5 less than 1 by 50 and 0. This can be written like this. This is the modulus notation. The absolute value of x minus 5 lies between 0 and 1 by 50. Now suppose I started from here. This is the limit. I'll call it L. This is the deviation 1 by 10. I'll call it epsilon. This is the symbol epsilon in mathematics. This is 1 by 50. I'll call it delta. Okay. Now every time I cannot say 25, 1 by 10, 1 by 50. I need to use symbols. So limit I'll be calling L. This I'll be calling epsilon. This I'll be calling delta. Now let me develop a definition. Now let me see if you can get that. Now I am saying that limit x tends to a. Now here x was going to 5. I say limit x tends to a of the function is L. Okay? Limit of the function x going to a is L when for any epsilon greater than 0. Now just keep this in mind. For any epsilon greater than 0, I took it to be 1 by 10. This was the epsilon, 1 by 10. For any epsilon to be greater than 0, there exists, this is the mathematical sign of there exists. There exists a delta positive. Now what you saw here, and I got this 1 by 50, that is the delta. So what I explained, I am translating into mathematical language. That for any epsilon positive, that was my 1 by 10, I must get a delta. I got the delta, that was 1 by 50. So that whenever x minus a lies between delta and 0. Now again, start from the beginning. For any epsilon 0, that was 1 by 10. I must get a delta, that was 1 by 50, so that whenever my x lies between that delta, plus and minus, so that whenever x minus a lies between 0 and delta, we have fx minus L less than epsilon. Now let's repeat this. This was the definition. I again take a look here and take a look at the numerical illustration, you will understand. For any epsilon less than 0, that was 1 by 10 plus minus. there exists delta, and there existed a delta that was 1 by 50. So that whenever I choose any value here, x, in this case 1 by 50 around 5, so x minus 5 lying between plus and 1 minus 50. So whenever I choose a value in this, then my function deviates from the limit only by an amount less than the epsilon. So this is why what I just explained. I'll repeat for the last time. For any epsilon 0, in my case 1 by 10, there exists a delta, in my case 1 by 50, that whenever I put my independent variable between this plus and minus 1 by 50, there is a guarantee that my function will lie within the bounds of the limit by an epsilon. So this is the proper definition of limit. Now this is written in textbooks, and the first look at this will be very perplexing, but this is not difficult at all. So this definition was given by the French mathematician So this is one of the celebrated definitions, and this is also used in the higher mathematics in the analysis. And also you need to familiarize, don't bother much about this, but at least you should have some feel of that, right? So this is how we explain the limit, that whenever there is a limit, we take our function a little away from the limit. It has to be guaranteed that the point at which we are investigating a limit deviates by a little. So we can create a neighborhood here and we can create a neighborhood here. If we can do that, that means the limit exists. So this is the mathematical logic behind the existence of the limit. So this I explained in case of y equal to 5x. And now what you find interesting, that our epsilon was 1 by 10 and our delta was 1 by 50. So in a way, our delta was 1/5 of the epsilon. So we exactly define our delta and the epsilon. Now, I take another example to explain this. Okay, take a function y equal to x sine 1 by x. Now I have already proved graphically that the limit of this function when x goes to 0 is 0. We have already explained this. Now somebody asked me that prove this by this epsilon delta argument. The argument I just explained, the logic that I just explained, sorry for the selection of the board, the logic that I just explained, that somebody can say that, okay, prove me that 0 is the limit of this by that epsilon delta argument. Now let me try. I told you what? That the function should deviate from the limit by less than epsilon. This is okay? The function should deviate from the limit by epsilon. Now, let us allow the function to deviate from the limit by epsilon. Can we find a delta? If you can find a delta, then it's okay. If you can't find a delta, then there is a problem. Now, put your function here. X sine 1 by x minus the limit is what? 0. We are claiming that the limit is 0. Alright. This should be less than epsilon. Okay, leave it here. Now, let me proceed, then I'll bring it back. This is what? This is x sine 1 by x. Now, you remember what I told you some time back? That you should always try to bring x within the modulus sign, because then you will find your delta. And your x here is going towards 0, so we should get something like x minus 0, which is already there. So, This is x sine 1 by x. Now, this is equal to this. This is equal to this. Now, this is equal to modulus x modulus sine 1 by x. This is simple. There's no problem. The modulus of two things is the product of modulus of them separately. So modulus x modulus sine 1 by x. Now, sine moves from where to where? -1 to +1. So the modulus moves from where to where? The modulus moves from 0 to 1. So this is either positive and this is a fraction and this is at the most 1. So this part is 1 or less than 1. So this is multiplied with something which is at the most 1 or less than 1. So this should be less than equal to this. Alright? Now, this is what? This is x. This is x. So, function minus the limit and we have manipulated and we have got it to be x. Now see, if this is less than this is less than this is finally less than this. Now, this is the value of the function and this is less than or equal to this. So the greatest value of this is x. The greatest value of this is x. And since this is less than epsilon, this is also less than epsilon. Okay? That means if this is less than half, this is also less than half. So what I'll do, I'll choose my delta to be same. Now the meaning is that I have chosen epsilon equal to delta. In the last case, delta was 1/5 of the epsilon. Now in this case, epsilon is equal to delta. That means the function is moving from the limit by less than epsilon. I'll choose the same epsilon and argue that because I have proved that x is the maximum value of this and I'm taking the deviation of x from 0 because I'm checking the limit at 0. So the function is deviating from the limit by epsilon and x is also deviating from the same value. So let's make epsilon and delta equal. That guarantees the existence of limit, because if this is half, this is also half. If this is 1 by 3, this is also 1 by 3. By choosing epsilon and delta equal, here we have proved that the limit also exists. So in the last case, delta was 1/5 of epsilon. In this case, simply delta is equal to epsilon. But the important thing is that the deviation here is by epsilon and the deviation of x is by delta. We have chosen delta and epsilon to be the same. So here also the limit exists. Now, let me show you cases where the limit does not exist. Now this is again slightly tricky, but let me try. Take a function fx which is 1 when x is positive and the function is -1 when x is negative. I am using the function which is 1 when x is positive and which is -1 when x is negative. Now, does there exist any limit? If you make a graph, this is very simple, but going by this epsilon delta argument, let's try to prove this. So in mathematics, what is done that you prove a few things with the help of the contradiction. Now I'll apply the same concepts, and let's say that there is a limit. I'll argue in this case that there is a limit. Now, suppose the limit is L. The limit is L. I'll take a particular limit and that limit is L. No matter where x is going, the limit is L. Alright. Now, if there is a limit, what is the meaning? The meaning is that my function deviates from that limit by epsilon. This is the argument. The function deviates from the limit by epsilon. For a certain time, let's assume that this epsilon is half. I can choose this. I told you that epsilon has to be positive. I am taking that epsilon to be half. Okay, you can take it anything else that you like, 1 by 3, 1 by 4, 1 by 5, whatever, but I am taking it to be half. So my functional values will deviate from the limit by half. Alright? Okay. It means I will get a delta. As the argument goes, that whenever this is the case, I'll get a delta. Okay? Now, suppose I check the limit at 0. Suppose I check the limit at 0. So if there is a delta, that means I can go till here and I can go till here. This is okay? Now, suppose I take a point in the middle here. That is what? Delta by 2. And here, that is what? Minus delta by 2. Right? I can go till this limit, or I choose one point in between. Delta by 2 and minus delta by 2. Now, what is my functional value at delta by 2? Now tell me. You see that I have defined, you see, delta by 2 is positive. So when x is positive, function is 1. So f delta by 2 is 1. And what is f minus delta by 2? When delta by 2 is negative, when x is negative, we have got minus 1. So this is what? This is minus 1. Now a little algebra here. This is clear? There is no problem? Okay. So f delta by 2 minus f minus delta by 2. How much is this? F delta by 2 is 1 and f minus delta by 2 is minus 1. So the subtraction will give you 2. It will give you, this is 1 and this is minus 1. So 1 minus minus 1 will be 2. So this is 2. So that means the absolute value of this is how much? 2. Okay? Alright. So this means that if I define my function like this, I take my limit to be something which is deviating and its deviation to be 1 and 2 half. So this means I can get my delta around 0 and then I do this calculation. Okay. Now see what I do. Modulus f lambda by 2, sorry, this is delta by 2 minus L plus L minus f minus this. I can write like this. Within the modulus sign, minus L and plus L. Shouldn't make any difference. Now, this is, I can separate it. Now this is the result. You must be knowing that when I separate it, it will be less than or equal. So this is what? F this minus L plus L minus F this. This should be okay with you. Now, this is less than this, F this minus L plus, I can swap it because this is a modulus minus L. Now see here. This is your function and I have defined that the function deviates from the limit by how much? 1 by 2. So this is what? This is less than or equal to 1 by 2 plus 1 by 2. This is what? This is less than or equal to 1. So what happened? I started with 2, I ended with 1. I got the result that 2 is less than or equal to 1. Now why this contradiction? Because I cannot apply the epsilon delta argument here. The limit does not exist. because if I forcefully create an epsilon 1 by 2, I create a delta around 0 or around any value, and if I can forcibly apply it, I reach an absolute result. So this means that if I create a neighborhood of half, I cannot create a corresponding neighborhood. That is not possible, no matter what value you choose. So this shows that with our epsilon delta argument, the limit does not exist. So this is one case. I'll finish this with another case. So these are the cases where your concepts get strengthened, and you should pay attention to that. Now one more example which I think should make the things clear. There is a very famous function in mathematics that is called now he was a very famous German mathematician. So you'll excuse me, I don't know the correct pronunciation. It is Dirichlet or it is Dirichlet. I'm not sure about that, but I'm sure about the function that he gave, and that is the good thing. So the function was fx equal to 1. Fx equal to 1 if x is rational, and fx equal to 0 if x is irrational. Okay? Fx equal to 1 if x is rational, and fx equal to 0 if x is not rational. Now, is there a limit? Now, apply the delta and epsilon argument. Okay. Now, what is the meaning of this? The meaning of this is that, let's see, this is 0. Suppose I check the limit here or anywhere, it doesn't make a difference. X, y. Now, this function tells you that if you choose a value here that is rational, so your function is 1, but at its side you choose a value which is irrational, the function goes to 0. Then at its side it's again a rational, irrational, rational, irrational, so 1, 0, 1, 0, 1, 0, so this keeps on fluctuating, right? So this is a very interesting function. This keeps on fluctuating between 0 and 1, and no, it's just your desire how fast you want it to fluctuate. It will fluctuate because you can always locate rational and irrational side by side. Okay, so by your intuition you must have realized that